Okay, so this problem is fairly lengthy, but essentially we are given a situation in which this rigid uniform horizontal bar is being, which has a mass m2 on one end, is being kept in static equilibrium by the various forces that are being applied on it, those being the string B, string A, M1, M2, etc. That's good to keep in mind. One of the key things from this unit that we recently learned was the fact that during static equilibrium, net force and net torque are going to equal 0, but in this case, we're going to utilize net torque to do what the problem is asking us to, which is solve for the tension in string A. And as we go through the work, you'll see how we can do that using that idea of static equilibrium to isolate T of A, or the tension in string A. So, as I said, since we know it's static equilibrium, we can set it equal to 0. Notably, since we're looking at torque, we have to pick a pivot point, and in this case, I used the pivot point as being where string B is located, and that's just due to the fact that string B isn't one of our variables, as you can see at the bottom of the problem, and when you put the pivot point over that force, it allows it to cancel out, meaning that the only things that are contributing torque to this situation now becomes the tension in string A, the force of gravity via M1, and the force of gravity via M2, or the torque due to gravity, rather, of those two. So it's also good to keep in mind, and this will come up in a second, that R in this equation that we've been given so often in this unit, torque equals RF sine theta, R is the distance from B to force, or rather the pivot point to the force, which is going to be pretty simple for string A and M2, but for M1, you might make a mistake and assume that R is L rather than L over 2. But due to the fact that L over 2 is the center of mass, it's going to be the notable point where the force is directed, is at that part, L over 2. So also notably, considering this equation contains sine theta, we have to figure out if the angle between the radius and the force changes the situation in a significant way. And you can see by the picture that for each of these forces, that angle is going to be 90 or negative 90, which is essentially just going to be either 1 or negative 1, which tells us that when we set this problem up, we're going to have to make either string A positive and the other two negative, or vice versa. So luckily the theta isn't too complicated in this situation. But now we can kind of move on and start solving. So once again, just based on the static equilibrium thing, we can just sum up the torques from these. And I went ahead and, using the variables from the picture, I solved for the torque that each of the notable torque forces, I guess, are contributing to. And so you can see in string A, it's distance times, or it's D times the tension in string A, and in M1, it's M1 times G times L over 2, which I already discussed earlier, why it's going to be L over 2 in this situation. And then for for the torque of M2, it's M2 times G times X. So now we can just plug all of those in, being equal to 0, and you can see in this case I made that tension positive, but like I said, it's kind of, you can do either the tension or the forces that are directed towards gravity or towards the center of the earth or whatever. just as long as you have them reversed. And I just did some algebra and solved that in this case, the tension in string A is equivalent to G over D times M1 times L over 2 plus M2X. So that is the end of this problem. Thank you for listening.